Section 3.5 has us change things up a little bit. So far in Chapter 3, what we've been doing is polynomial functions, right? And you see that the title on 3.5 is that we're looking at rational functions. Rational functions differ from polynomials in the fact that they are ratios. They're actually ratios of polynomials. So you end up with a polynomial on the numerator and a polynomial on the denominator. Now, sometimes those polynomials in the numerator are very unexciting, like the first example, 1 or -1. So our polynomials are not very exciting sometimes, but they're still considered a polynomial on top and on bottom. Now, our first set of questions have to do with domain. So you'll remember we've talked about domain in a number of contexts before. We've talked about it from looking at a graph. We've talked about it in terms of polynomials. We've talked about it in terms of piecewise functions or linear functions as well. We've done it in a variety of contexts. This time we're going to talk about it for rationals. So in particular, when we're looking at what x values are allowed, for rational functions, it's actually a better question to ask what x values are not allowed. So in particular, if you have a denominator, what value can the entire denominator not equal? 0. And the reason is because if we attempt to divide by 0, we get an undefined value. Division by 0 is not a defined operation. So we cannot have denominators equal to 0. So when we're looking for domain, instead of looking for what x can equal for rational functions, we're instead going to ask ourselves, what can x not equal? And in particular, what that means is it means what places can we not have the denominator equal to 0. So we're going to take our denominator each time we're working with these for domain, and we're going to set it to be not equal to 0. So in this one solves very quickly. We find very quickly that the problem spot, the thing that cannot happen, is that x cannot equal to 2, right? If I were to put 2 in the denominator, you probably could look at that and just eyeball it and have told me that too, and that would be totally fine. 2 is the problem spot. So if you think about this from a number line perspective for the moment, so that we can get a glimpse of how to think about our inequality, what we have is we have everything bigger than 2 and everything smaller than 2 allowed. So we're writing this always in interval notation to say that we're going to start at -infinity and go to 2, but we're not allowed to use 2, and then we're going to pick back up at 2 and go to infinity. Parentheses, yeah, well, for what we're doing here, yes. You're going to end up with lots of parentheses. Very, very typically parentheses that are going to be involved. Because that's my domain. So again, domain means finding what x can equal. But what that sort of means as the sort of flip side is that if we decide what x can't equal first, we can then write what x can equal. It's everything but 2. Now, on the second problem, right, we don't have a linear function on bottom. It's quadratic. So I'm starting it the same way. I want to know where this denominator cannot be equal to 0, right? I want it to be not equal to 0. But I can't solve it directly, shift things over, divide, and be done, or whatever. I still have to factor just like I do when it's equal to 0. If I'm trying to find where this is equal to 0 or not equal to 0, I do it the same way. So I'll factor if it can, or quadratic formula if it can't. This one factors, so I have x and x, 12, -12 specifically. So the negative at the end tells me I need 2 different signs. I need 2 numbers that multiply to -12 and add to +1. +4 and -3 will do it. Is that good for everybody? Okay. So again, we set each of these to be not equal to 0. So x minus 3 is not equal to 0. X plus 4 is not equal to 0. And if I add my 3, I get x cannot equal 3. And if I subtract my 4, I get x cannot equal to 4. Oh, I'm sorry. Yes, thank you. Get that negative in there. Thanks. Okay, you can actually go straight into writing the inequality notation, I mean, the interval notation if you wish. That's totally fine. But sometimes it's a little bit easier to see if you do a number line, especially if you're a visual person. I personally see things very well from a visual perspective, lots easier for me. So I'm going to draw the number line, and you can recognize that that's sort of an optional step. I need to make sure that my numbers are in order. That's very important for writing your interval. -4 comes before +3, right? And I want to represent all three of these intervals, both before -4, between -4 and 3, and after 3. So when I'm writing my interval notation, I'm going from -infinity to -4, again with those parentheses like you mentioned, Bailey, between -4 and 3, and then after 3. The most common error that I see when I have problems like this given is missing one of those three pieces. In particular, it's usually the missing piece between, the -4 to 3 piece. So number line will help you to keep those pieces all in order if that's causing you some trouble. Okay, any questions on that? Domain. Now, we're going to have that domain related to another idea. And that idea is asymptotes. So there are two different kinds, well, there's three different kinds of asymptotes, two that we're going to talk about in this lesson. The first type of asymptote is called a vertical asymptote, and I will show you pictures of all these later when we work on our graphing for these. But for right now, just definitionally, first you have to get your rational function into lowest form. So if we were looking at the number 1 here, it's in lowest form because the numerator can't factor. But number 2 may or may not be. If I were doing this on number 2, I would have to factor the top and see if anything cancels out. And it might, right? So we would want to be careful about that. So finding vertical asymptotes necessarily involves factoring top and bottom, whereas the domain didn't need that. So I factor the top and bottom, reduce if I can. And then our vertical asymptotes will be the locations where the reduced denominator is equal to 0. Much like over here where I took my denominator and set it to be not equal to 0. Okay, so I need to reduce it first, but then if it's in reduced form, then it's where the denominator is equal to 0. They will have equations x equals a number. This is really important. I cannot tell you how many times that I have students tell me the vertical asymptote is 7. No, it's not, because 7's a number. It's not x equals 7. So you have to write the x equals part. That's what makes it an equation. So vertical asymptotes require us to do a little bit of work. Horizontal asymptotes are an identification type of a question. Horizontal asymptotes are based upon the degree on top and the degree on bottom. So there's 3 possibilities. The first possibility is that the degree on top is larger. We haven't seen one of those yet. The second possibility is that the degree on the denominator is larger. That happened in the first problem. I promise I'll switch back. You guys keep writing in just a second. Take a look at the degrees on the top and the bottom of problem number 1. What's the degree on bottom? 1. We see it there. It's x to the power of 1. What's the degree on top? It's 0. So Bailey had me for intermediate algebra. We talked about that in there, so I know that's what she's remembering it from. So hopefully you remember that too. If you just have a constant on top, its degree is 0. So this one is a case 2 problem. The degree on the denominator is bigger. The last option is that the degrees are the same. If the degrees are the same, it looks like problem number 2. Again, I'll flip back. The degree in the numerator on problem 2 is a 2, and the degree in the denominator on problem 2 is a 2. So let me tell you what happens in each one of those cases. If you have the degree on top larger, then it means that there is no horizontal asymptote. And I'll abbreviate it HA. There's no horizontal asymptote if the degree on top's bigger. Something else will happen. We'll encounter that later. But there's no horizontal asymptote. If the degree on bottom is bigger, then your horizontal asymptote is y equals 0. So over here on this problem, if we had been looking for horizontal asymptotes, the horizontal asymptote on this one is y equals 0. The degree on the bottom is bigger. Okay, we'll talk about what this does in terms of a graph, I promise. The last one, if the degrees are the same, is the most difficult one to write down, but it's not difficult to do. It's still y equals. And it's y equals the ratio of the leading coefficients. So we're going to flip back to that example number 2 so that you can see it in play. Degrees are the same, top 2, bottom 2. So my horizontal asymptote is y equals, and it's the coefficient on top, which is a -1, divided by the coefficient on bottom, which is a 1. So -1 divided by 1. So my horizontal asymptote on problem number 2 would have been y equal -1. Okay, so it's not hard to do it. It's just kind of weird to say it. It's just like it shows up in the fraction to begin with. Exactly. Degree of numerator, leading coefficient, and then the leading coefficient of the denominator on the denominator. Okay, so we're going to do a couple problems now from scratch. We're asked to do more than just asymptotes, but that's the new piece of information we're asked for. Okay, so here's an example. We're asked to do 3 things. We're asked to find the asymptotes, we're asked to find the intercepts, and we're asked to sketch the graph. So, asymptotes, that's new. That's where we're going to start since it's listed first. So my asymptotes, there are 2 types so far that we've looked at, horizontal and vertical. I'm going to start with horizontal because it's an identification piece. I don't have to do a lot of work for it. I just have to identify it correctly. Where is the degree larger, top or bottom? Yeah, the denominator has the larger degree, right? So which case am I in, 1, 2, or 3? 2. So I automatically know then that my horizontal asymptote is y equals 0. Not 0, y equals 0. Vertical asymptote takes a little bit of work. Now, if the fraction weren't reduced, we would reduce it now. But this one is reduced because all I have on top is a 1, right? So I don't have any reducing to do. So what that means is that I'm at the point where I simply set the denominator equal to 0. So it's much like finding the domain at this point, except that it's equal 0 instead of not equal to 0. So if possible, and most of the time that's the kinds we work with, we factor. So x and x. The positive 6 at the end tells me that my signs are the same. The -5 in the middle says they're both negative. I need 2 numbers that multiply to 6 and add to -5. -3 and -2, you bet. So I'll set each one equal to 0 and solve. So x equals 3 is one of my vertical asymptotes, and x equal 2 is another one. Before I go any further, I want to show you what asymptotes look like when you graph them. Let me make one word of caution. If you do have a graphing calculator, I'm definitely not telling you you cannot use it. But what I am telling you is that it's not very helpful for graphing rational functions because it won't put your asymptotes in, which means that you're going to be left giving me something that's going to be very obviously not work done by hand. And it's going to be incomplete at best. All right? Sometimes, at worst, it connects things that shouldn't even connect because asymptotes throw it off. Programming problems and so forth, okay? So, on this one, yes, sir? That's okay. So horizontal asymptotes are all about deciding which of these three cases you're in. On this case, my degree of my denominator is a 2, and my degree of my numerator is a 0. So the degree of the denominator is bigger, which means that I'm in case number 2. So my horizontal asymptote is 0, y equals 0. Okay. All right, so asymptotes you're going to draw as dotted lines. I'm going to draw mine as a green dotted line. The first one is y equals 0, and y equals 0 is the same as the x-axis. So this is my horizontal asymptote, drawn dotted in. So descriptively, what is an asymptote? Well, an asymptote is a line that you get close to and don't touch. And that's the basic idea. There is a caveat to that. Occasionally, you will cross the asymptote, but only towards the inside of the graph. Asymptotes really are about what happens, horizontal asymptotes, on the end behavior. What happens towards the end of the graph? So it's kind of like when we were doing the polynomial questions. What are the end behavior? They both point up, they both point down, there's one of each, right? We have those 4 options, basically. Here, they're going to be leveling out somewhere. They level out at the horizontal asymptote edges. Now, when we have our vertical asymptotes, those are also lines that we do not cross. But we absolutely never cross those. There's not any middle part of them because they don't go towards the edges of the graph. So I'm going to make them kind of big because 2 and 3 are kind of close together. So imagine that this is my graph then, okay? And my dotted line go a little further out here. We have our vertical asymptote at x equal to 2. And that should look vertical and not slanted. And at x equal to 3. Okay? Those are the dotted lines we put in from finding asymptotes. Are we good so far? Now, they're not really a part of our graph. That's why your calculator doesn't put them in when it graphs it. But they are part of the representation that you need to draw so that you can draw the rest of it properly. So the other thing that we're supposed to do besides finding asymptotes is find intercepts. We have found intercepts before for different types of functions. Not for this one yet, so my intercepts. One option, or one type of intercept, is the x-intercept. If you'll remember, the x-intercept means y equals 0. Well, y is the whole function. So this is 1 over x squared minus 5x plus 6. When we have rational functions, a rational function will only equal 0 if the numerator can equal 0. And the reason is because no matter what I put into this denominator, like this one has a numerator of 1, no matter what I put into this denominator, I cannot take the number 1 and divide it by something and get 0. That is not possible, right? I'm always going to get a rational number that doesn't equal 0 when I do division. So this doesn't work. There is no place for that to be possible. So that means that there are no x-intercepts. It will never cross the x-axis on this graph. And that kind of makes sense in terms of the dotted line on the x-axis here, right? So this one's asymptote along the x-axis is actually never going to be crossed. Not even in the middle where I might have been able to, depending on the equation I had. Our second one, our y-intercept. Our y-intercept is when x is equal to 0. So I have 1 over 0 squared minus 5 times 0 plus 6. What will that give me? Yep, 6 on bottom, so 1/6 in general, right? The whole thing. So I need to cross the y-axis at 1/6. So, like about right there, give or take. Here's the cool thing about these graphs, rational functions. You don't need a whole bunch of points to be able to plot to graph this thing. You need 1 point in each area. So what do I mean by area? Well, my asymptotes, my vertical asymptotes, divide this graph. They divide this graph into the things that occur before x equals 2, the things that are in between 2 and 3, and the things that are happening after x equals 3. There are 3 regions that I have divided this graph into. What that means is that I need a point plotted in each of those 3 regions, and that's all I need. 1 point's enough. Now I already have a point plotted in the first region. Let me erase all this. I plotted it right here. Agreed? I'm going to plot a point in each of the other regions, and then I'll show you how we can use those points to give our graph. So the first point plotted in the first region's enough. We need a point that happens to be between 2 and 3. I'm going to pick 2.5. And we need a point that's bigger than 3. I'm going to pick 4. So I'm going to take the number 2.5 and I'm going to plug it into our equation. So I'm going to g of 2.5 equals 1 over 2.5 squared minus 5 times 2.5 plus 6. And if you plug that in, your calculator will tell you that this is equal to 4. I think it's negative 4. I did it in the last class. Let me double check. Yeah, negative 4. And we'll do the same thing for the point at 4. X is equal to 4. So I have 1 over, I do 4 squared, minus 5 times 4, plus 6, and it gives me 0.5. Okay, so at x equals 2.5, I have negative 4. That's about right here. And at x equals 4, I have positive 1/2. So about right here. Okay, the 3 dots are in 3 separate regions. This is not connect the dots. I have to pay attention to my asymptotes. They give me the direction for the general shape. So if I'm taking the first point and I'm moving left, right, what happens before my y-intercept left? Well, it has to get close to the x-axis because it's an asymptote, so it looks like that. And if I move from that y-intercept to the right, it has to get close to the next asymptote, which is a vertical one right here. So the graph looks like this. Now, my second dot has to get to the asymptotes on either side of it as well. In theory, it could go up or it can go down. Why can it not go up? Yeah. If it were to go up, what would it eventually do? Cross the x-axis. And I already said there's no x-intercepts, right? So it has to move away from that asymptote. It can't touch it. So it looks kind of like a parabola that's sandwiched in between asymptotes. It's very narrow. The last dot at 4. If I move to the left, I have to get close to the asymptote right here. And if I move to the right, it will taper off at my asymptote that's on the x-axis, y equals 0. So now, if you looked at your calculator, and you might have to shift the zooming window and things like that if you're looking at a graphing calculator, it will look similar to this. It won't draw in the dotted lines, none of that will be there, but you'll see these kind of arches. What I was talking about some of the calculators doing is that some calculators will do weird things where it will, I'll draw it in a different color so you can see what it's doing. It will try to connect this with this, and you'll see these sharp turns like this. Or you'll try to connect this with this, and it'll look like that. Like it'll all be connected. It will try to connect the dots. The dots can't be connected because there's asymptotes there. So our graphs should not have that in there, even if it looks like your calculator is trying to do so. Any questions on this first one? Okay, we have one more today to be at the same spot as our other class. Same directions. Asymptotes, intercepts, sketch the graph. So we will start with, just like last time, our horizontal asymptote, because it's an identification feature. What can you tell me about the degree of the numerator and the degree of the denominator? They're the same. You're right, Elijah. They're the same. So if they're the same, we're in case number 3. Case number 3 is a ratio. Again, it's y equals, always y equals. What is the leading coefficient of the numerator? 2. What's the leading coefficient of the denominator? 1. So my horizontal asymptote is at y equal 2. Okay, so we're going to shift our focus now to our vertical asymptotes. And we haven't seen one yet where we've had to, and we still didn't see one yet here. But this one's in reduced form. I know it's in reduced form because they're both linear and I can't cancel out a factor from the top and bottom. All right, cancellation always occurs in factor pairs, right? It's in a grouping, and there's no factorization that cancels here. So, if that's the case, I take my reduced denominator, which is my original denominator, and I set it equal to 0, and I solve. So my vertical asymptote is x equal 1. Again, not 1, x equal 1. Okay, so I'm going to pause and draw the asymptotes first, and then we'll come back and do our intercepts. I need a horizontal asymptote at y equal to 2. So something like that. Let me shift it up a little. And I have a vertical asymptote at x equal 1. Okay. How many regions do I have? Looks like 4. It's not 4. It's just 2. It's not all the pieces that all the asymptotes cut it into. It's only where the vertical asymptote cuts. So in a moment here, when I start to graph the whole thing, I have one region that goes to the left of 1 and another region that goes to the right of 1. There are only 2 regions because my vertical asymptote only splits the graph into 2 regions. Okay, so I will only need 1 point before the x equal 1 and 1 point after x equal 1. Let's see what my intercepts give me in terms of points already. So we'll start with x-intercept. So x-intercept is when y equals 0. That's actually possible on this one. So this is my y, f of x is 0. I have 2x plus 4 on top. And I have x minus 1 on bottom. Notice if you cross multiply, what's going to happen to that denominator? It's going to cancel. It goes away. So it really does always become, for my x-intercept, where does the numerator, in fact, let me just write that in there, where does the numerator equal 0? Because I'm going to get 0 on the left, or on the right either way, and 2x plus 4 on the other side. It's just where the numerator is equal to 0. So 2x plus 4 equals 0. I'll subtract my 4. 2x equals negative 4. And divide by 2. So x is equal to negative 2. Okay, that's an x-intercept. I'm going to go ahead and plot it, and then we will come back to the other piece that we need to find. The x-intercept of negative 2 would be over here. Okay, so that's actually enough. If I were only asked to plot to graph it at this point, I don't even need to find the y-intercept to do this particular problem. I'd have 1 point on the left and be enough. But I am going to have another point on the left somewhere because my y-intercept is obviously on the left-hand side of x equal 1. So I'm going to get an additional point, and I'm asked to find it, so I need to find it either way. So my y-intercept, namely when x is equal to 0, will be y equals, I have 2 times 0 minus 4 over 0 minus 1. It's 4 positive in the numerator, sorry, 2 times 0 plus 4 over 0 minus 1. Okay, so the numerator becomes a 4, denominator is -1, and my y-intercept then is at -4. Okay, so my y-intercept is at -4. I do need to do one more thing here. So here's my -4. My x-intercept and my y-intercept should be listed as ordered pairs. I'm so sorry I did not write that before. So this is the 0, -4. It's an ordered pair. This is -2, 0. That's my x-intercept. This one's my y-intercept. Over here, I didn't write it that way either. I didn't have an x-intercept, but my y-intercept was 0, 1/6. If it didn't specifically ask for it, it wouldn't be mattering, but it does specifically ask for it. Okay, so on the left-hand side of x = 1, I have 2 points. Obviously, they are going to be connected. It is connect the dots because I'm in the same region. But I have to use my asymptotes to give guidance to how I'm going to draw them. So these obviously get connected here. And it's not a straight line connection or it won't be smooth. And then before the x equal to -2, it has to get close to the asymptote above it. So it looks like this. And after that y-intercept, it has to keep going down and getting close to that that vertical asymptote at x = 1. So it looks like that. I really have 2 options. My graph will either look like this, roughly speaking, or like this. I mean, those are the only options that I have in order to get close to both of those graphs. The reality is, I know it's not the one that's currently drawn. How do I know? Nope, they don't always have to be opposite. It's a good guess. A lot of times they are. If it were drawn like this, what would I have? I'd have another x-intercept, which I don't have, right? I don't have another x-intercept, so I know it has to be up here somewhere. So that's sort of just a cognizant awareness kind of thing that you should be aware of. That's our expectation. So we do need to find one more point. You can pick whatever point you want. I'm going to pick x = 2. And we're going to put 2 into our equation. Let me just do it above so I have more space. F of 2 is going to be 2 times 2 plus 4 over 2 minus 1. 2 times 2 is 4 plus 4 is 8. And then 2 minus 1 would be 1. 8 divided by 1 would be 8. So at 2, I'm at 3, 4, 5, 6, 7, 8. I'm really high up. That was bad. Let's try again. That's better. So I'm at 8. So it's 2, 8 right here. Almost off my screen. And again, it has to have that same feature where it's getting close to the vertical asymptote and close to the horizontal asymptote. And if it helps to extend your asymptotes to give a picture that makes more sense, please do that. All right, I can't get it quite drawn, but that's okay. Any questions on that one? All right, we will pick back up in section 3.5 next time. Have a great weekend.